Hello and welcome to our lesson on the law of cosines. So this is going to kind of build what we did in our previous topic with the law of sines was find ways to solve triangles. Right? If we were given some information about a triangle, we could use the law of sines to find the rest of the information. Now, the law of sines is only useful if particular information is given. So we can use the law of sines formula. We can use the ratios that are in the law of sines when we're given any two angles and a side. So angle, angle, side, or angle, side, angle are ways to describe two angles and a side. Or if we were given two sides and a non-included angle, the side-side angle. Now that one did lead to an ambiguous case or a no triangle and no solution case, but we could try to apply the law of sines with that information. If we're given side, angle, side, so two sides and an included angle, or side, 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 all three sides and no angles, the law of sines isn't going to be possible. And if you don't believe me, which you probably do, but I just want to show you why it wouldn't be possible, okay? So let's say we had a side, side, side case. That's what we have here. If we knew the three sides of a triangle, I could not use the law of sines to solve for anything. So when I'm using the law of sines, let me just choose two ratios here, right? I would choose two of my ratios set equal to each other. In order to solve an equation like this, any equation, right, I have to have just one variable in that one equation. So I would have to know at least one of the angles and then two of the sides to find a missing angle, or I would have to know at least two angles and one of the sides to find a missing side. So if I don't have any angles, it's not going to be possible to use the law of sines. And the same will be true if I wanted to try to find or try to use law of sines with the side angle side case. So that's when you have two sides and the included angle, so the angle's right between it. Again, if I want to try to use the law of sines to solve here, I have two sides, but it's not the right side. So, for instance, let's say that this was A here, but I don't know the side that's opposite of it. I have to know one of these fractions, and one of these can be an unknown, but I have to have at least one of my ratios. So if this is the angle that I know, I have to know the side that is across from it in order to set up one of my ratios. So I just don't have enough information if it's side, 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 or side, angle, side in order to apply the law of sines, which is where the law of cosines comes in. So if we have the side angle side case or the side 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 case, then we have three different laws here, three different depending on what angle and sides we're given, or what angle and sides we want to solve for. If we have side angle side or side side side, one of those formulas can be used to solve our triangle. Now before we go into using those formulas to solve, it's helpful to know a little tidbit about triangles. It's helpful to know that the angle measures and the side lengths that are opposite of them, they correspond. And what I mean specifically is they don't just correspond in labeling, like capital A, capital B, little b, but the longest side is opposite of the largest angle. And similarly, the shortest side is opposite of, it is across from the smallest angle. This is helpful information to know that the side lengths and angle measures, they correspond in size, okay? And when we're using the law of cosines to solve for an angle, it's going to be helpful for us to solve for the largest angle first. Now, why on earth would we want to know the largest angle first? This isn't like a set rule. It's not necessarily true that we have to find the largest angle. It's just helpful because once we know the largest angle, we're sort of guaranteed facts about the other two angles, the two remaining angles. So for instance, if we calculate our largest angle first, and that largest angle happens to be obtuse, well, a triangle can only have one obtuse angle. So if we calculate our largest angle and it's obtuse, it guarantees that the remaining two angles have to be acute. Okay, because there can only be one obtuse angle in a triangle. Now, if we go to calculate our largest angle and it happens to be acute, then the remaining two angles will also have to be acute. And you're thinking, wait, that doesn't make sense, but it does, because if our largest angle is acute, the other two angles have to be smaller than our largest angle, so they would have to also be acute. So once we know our largest angle, we're guaranteed that the other two angles are acute. So it gives us some direction when we're solving, or we want to eliminate that ambiguity, right? So let's try it out. Let's see if we can't use the law of cosines to find the three missing angles in this triangle. So it says determine the three angles for a triangle in which A is 3, B is 5, and C is 7. So I'm going to call this 3 and 5 and 7, and this picture isn't necessarily to scale. I just put a triangle there for helpful reasons. Okay, so trying to be helpful. So this would be capital A because it's across from C, which means that is my smallest angle because that is my smallest side. And then this is going to be, let me change colors here. I'm going to call this capital A. And then across from 5 here, 5 was little b, so this is going to be capital B. And that's my mid-length side, so that's my mid-measured angle. And then across from the 7, right, this side is opposite of this angle, that was C, so that's going to be C there. Now, 7 is my largest side, which means C is going to be my biggest angle. So what I'm going to do is start by solving for angle C. And C is only coming up in the third version of our formula here, so that's the version that I'm going to use. And I wonder, I was going to copy and paste, but I know this formula. Okay, so we're going to use that third version of the formula. It says that C squared has to equal A squared plus B squared minus 2, and then it's going to be AB and times the cosine of C. And the way I remember these formulas, let me go back up here real quick. So these are, you can probably see a connection between these and some Pythagorean theorem. They sort of look Pythagorean theorem-ish. They are derived from the Pythagorean theorem. But what I like to remember is that we start, oops, I wanted my highlighter. We start and end with the same letter. So if we start with A, we're going to end with A. We start with A squared, we're going to end with cosine of A. And in the middle are the other two. So if we start and end with A, then we need B and C to be in the middle. So it's B squared, C squared, and 2BC. And again, here we're starting with B, ending with B, and then the other two, A and C, those are in between. So A squared, C squared, AC. And then in the last one, we start with C, end with C, and then the other two, A and B, those are what we see in the middle. So I don't know if that helps you, but that's how I remember these formulas. The law of sines is actually a pretty easy one to memorize if you use it enough, but here it is. So we want to solve for C, and that's capital C on this one. This is a little c over here. Let me make it a little smaller because it looked a little large. Okay, so we know all the information that we need to be able to plug in and solve for that one remaining variable that's going to be in there. So C squared, we're going to put 7 squared here, and then A squared is going to be 3 squared, B squared is going to be 5 squared, and that's 2 times 3 times 5 times the cosine of some angle C. So let's just math this out, alright? This is 49 here. We have 9 here, 15 here. Sorry, 15. My gosh, don't trust my math. 5 squared, I know that, is 25. And then I'm looking ahead. So 2 times 3 is 6, and 6 times 5 is going to make 30, so this is going to be minus 30 times the cosine of C. Well, 9 and 25 here makes 34. So 49, we're getting there, equals 34 minus 30 cosine of C. And maybe you can take less steps in the solving here, but the goal is to try to get that cosine of C by itself. Remember when we're solving a trig function, that's what we're doing here, solving a trig function. We want to try to isolate that if possible. So we're going to subtract over the 34, and 49 minus the 34. Let me just not skip anything out here. 49 minus the 34 is going to leave us with 15. And then we still have a negative 30 times our cosine of c. And now we're going to divide both sides by negative 30. Divide both sides by negative 30. And so at last, we have a negative 1/2 here equal to the cosine of some angle c. Now, I would argue that this is something that we should know based on our experience with the unit circle. Cosine's actually negative in 2 places, but those 2 places where cosine are, let me just draw this for you. Cosine is going to be negative here in quadrant 2, and it's also going to be negative in quadrant 3. But the angles that are in quadrant 3, they're beyond 180 degrees, so they can't be in our triangle. So we know we're going to be looking at an obtuse angle, because it's got to be an angle that's in quadrant 2, so it's going to be obtuse. So I know that. And if you can remember where that actually hits on the unit circle, then you'd be great. If not, we do have inverse cosine to solve this. So this says the cosine of some angle equals 1/2, which means that the inverse cosine of that negative 1/2 would tell us exactly what that angle is. So if you don't want to pull out the unit circle again, or if you just can't remember, it's totally fine. We can use our inverse cosine, and I can't read. Okay, sorry, of negative 1/2. And it's going to tell us, oh, that answer does not look right to me. Remember, your calculator needs to be in degree mode. And there it is, 120 degrees. So C is 120 degrees. Woohoo! All right, so now we got one. I know that this is an obtuse angle here of 120 degrees. That means we only have 60 degrees left in the triangle. So the other 2 angles are going to be 2 acute angles that add up to 60 altogether. So now the question is, how do you want to find the remaining angles? We could go about using the law of cosines again, but in my opinion, the law of sines is easier to use when we can use it. And we can actually use that here because I know a combo of an angle and the side that is across from it. So I'm going to use the law of sines here. I'm going to say, here, let me just the formula. The sine of c I can take now because I know the length of c. And that's got to equal a over a, sine of a over a, or whichever one. So I'm going to try sine of a over a first. Okay, so what I know in this one, the sine of c is going to be the sine of 120 over c. The length of c we knew was 7. And the sine of a, I don't know. That's what I'm looking for, but I know the length of little a is going to be 3. And so 3 times, if I cross multiply here, sorry, cross multiply, trying to skip steps in my head. It's a dangerous thing. 7 times the sine of a is going to equal, cross multiply here, 3 times, nope, pretty sure I said go back to red. Thank you. 3 times the sine of 120, and then we divide. So the sine of a is 3 sine of 120 over 7. And so if the sine of some angle is that, then the inverse sine of that fraction is going to be our angle. So a is going to equal the inverse sine of 3 sine of 120 over 7, and calculator time. So we want the inverse sine of a fraction on the top, 3 times the sine of 120, and hopefully we know the sine of 120 is radical 3 over 2, but that's okay. And then on the bottom is going to be 7. So just make sure I'm in degrees. Yep. That means that angle A is going to be approximately, and this answer makes sense. I knew it was going to be an acute angle, so let's say 21.8 degrees. Now we don't have to go through much work to get the last angle, because the 3 angles in a triangle have to make, what the heck? I don't know where 28.5 came from. I'm so sorry. I know that the 3 angles in a triangle have to make 180 degrees. So for my last angle, I have 180 degrees total. I'm going to subtract out the 120 and the 21.8. So that's 141.8. If I subtract from 180, what's going to be left is 38.2, I think. Let me not get this far and then mess up. That would be just a tragedy, right? 180 minus 120 and 21.8 and yeah, 38.2. Sometimes you never know, people. 38.2. I just copied over 21.8 as 28.5, so yeah, don't know if I can necessarily trust myself. All right, so there it is. Okay, we used actually law of cosines to get started, law of sines to continue, and then subtracting 180 to finish. But we were able to find all three angles in our triangle. All right, so that was the side, side, side case. Let us try the side angle side case. Luckily, we don't have to worry about any ambiguous cases here or no solution cases here. So in the next one, it says, this time determine the missing side and angle measures for a triangle in which A is 15, C is 7, and B is 160. So I don't really matter what's what here. But let's say this is 15, this is 7, and actually, let me label my angles first. Let's call this A. Let's call this B, call this C, and this, again, might not be drawn to scale, so don't worry about actually how the triangle looks. I just put it there so you didn't have to draw your own triangle if you were printing. So A is 15, that's across from A, and C is 7, that's across from C, and the measure of angle B is 160 degrees, so I'm going to put 160 degrees in there. So side angle side case, okay? So we actually already have the measure of our largest angle, which is great. That means the other two angles in the triangle have to be acute. But again, this is not something that I could use the law of sines on because I can't make a ratio of my angle to the side that's across from it. So I'm going to use a law of cosines. It doesn't really matter which angle we choose to use or which version of the formula we choose to use, which angle we choose to solve for. So I'm just going to go with looking for A because I chose C last time. So if I want to use A, oh my gosh, where am I going? Okay, let me go back to my formulas. Let's look at these here. I actually, if I want to be able to find the measure of an angle, I need to backtrack myself a little bit. If I want to be able to find the measure of one of my missing angles, I have to know all three side lengths. Doesn't matter which version of the formula I'm looking at. If I have to know all three side lengths, then I have to worry about finding a side length first. Okay, so let me go back to this problem. If I have to find a side length first, so this missing side, that has to be the first goal because all three sides are used in the formulas, which means because this is the only angle that I have to use the formula that includes angle B. So since I have to use the formula that includes angle B, then it matters where I start here, okay? I'm going to use the formula that starts with B. So B squared, because it's going to end with B, is going to equal A squared plus C squared minus 2AC times the cosine of B. And we know A, we know C, we know angle B. That's going to allow us to find that missing side, little b. Okay? So we are going to have B squared, this is our unknown. A squared is 15 squared. C is 7, so 7 squared. And then 2 times 15 times 7, and then the cosine of B, which we were given as 160 degrees. So there actually isn't too much solving here. This is really just going to go into the calculator, but to solve for B, we do actually have to take the square root of this nonsense. So 15 squared, 7 squared, 2 times 15 times 7. I'm not going to worry about doing any multiplying since I know I'm just going to put this in the calculator, and I am, mistake prone, so let me just calculator all of this. 15 squared. I just made calculator a verb. Yes, that happened. Sorry, minus 2 times 15 and 7. And then that's going to be multiplied by the cosine of 160. And let's make sure we're in, yep, still in degrees. And so we end up with B as approximately 21.7. 21.7. So now I can put 21.7 here. And Now that we've solved for that side, we've got options. We can use the law of cosines at this point to find missing angles, but I prefer the law of sines, really a matter of choice. So I'm going to go ahead and use the law of sines from here. I know that the sine of angle B over B, which we just found, has to equal, let's say, the sine of angle A over A. So I can say in this one that the sine of 160 over 21.7 has to equal the sine of A that I'm looking for over A, which we know is 15. And then I can cross multiply. So we're going to have 21.7 times the sine of A equal to here 15 times the sine of 160, and then we're going to divide. So the sine of A is 15 sine of 160 over 21.7, and then we're going to take the inverse sine to solve for A. So the inverse sine of this mess of a fraction here is going to get us an approximate value for A. So inverse sine of a fraction, 15 sine of 160 over 21.7 makes our angle about 13.7. So about 13.7 degrees. So I'm going to put 13.7 degrees in there. And then the last little bit, I know my angles in my triangle make 180. So if I subtract out the 160 and the 13.7 that's already in there, then what's left? Well, this is 173.7 altogether. So not much left. It's going to be, what, 6.3 degrees? And I'm pretty certain, but my confidence is just lacking. Minus, let's take out 160 and 13 points. So I just want to be sure. It's just would be a shame, like I said before, to get this far and then mess up on something so silly. Okay, so 6.3 degrees, and we're good. Triangle solved. Okay, again, by using a combination of law of cosines, law of sines, and angles in a triangle making 180 degrees. So as you've seen from the previous two examples here, or this example and the one before, the law of cosines could be used to find angles or sides just like the law of sines, but there are particular places where you're going to want to start. If you're finding all of your angles, find the largest one first, and if you're given one of your angles, then you're going to have to solve for the missing side first. Okay? So, from the two formulas, the two sets of formulas, the law of sines and the law of cosines, a pretty famous mathematician developed another way for us to be able to find the area of a triangle. Generally, when we're finding area of a triangle, what you should be thinking is 1/2 times base times height. And that's still true. That is still an acceptable, perfectly acceptable way to find the area of a triangle. However, sometimes all of that information isn't known. We may not know the base and height of a triangle. We may know the side lengths, and that, according to Huron here, is going to be enough for us to find our area. So Huron's formula, Huron, it's also said Huron, it's, you know, tomato, tomato, up to you. From the law of sines and law of cosines, there's a super fun proof for this. And when I say fun, that's sarcasm. If you want to look it up, I did not want to bore you with that one. But where the law of cosines and law of sines is used to derive this formula, it's an interesting one. It's a little too much for us, but we just have to be able to use this formula and know that it exists. Okay? The formula says if you know the side lengths, don't have to know anything about the angles, don't have to know the height. If you just know the side lengths of your triangle, let's say the sides are A, B, and C, what we can do is calculate a value for what we're going to call S here by adding those side lengths and dividing by 2. So if we have side lengths A, B, and C, add them up and divide by 2 and call that value S, then the area for our triangle is going to be the square root of that S times S minus A, S minus B, and S minus C. That is our formula from this mathematician. Okay, actually pretty easy formula to use. So let's try it out. One quick example here. Set designer is putting together a backdrop for a play, and one element of the scene is a large triangular piece of wood. Her assistant measured the side lengths at 4 meters, 7 meters, and 9 meters, but she wants to know the area of the triangle to estimate the amount of paint needed to cover it. So we're going to find the area. So we've got side lengths of 4 and 7 and 9. Okay, not that we needed the picture there, but there it is. So according to this formula, we would have to find S first, where we take the side lengths 4, 7, 9, add them together, and then divide by 2. So 4 and 7 is 11, 11 and 9 is 20, and 20 divided by 2 means S is going to be 10. So according to our formula, the area is going to equal the square root of, in the front here, we've got 10. And then here, it's S minus A, one of the side lengths. So I was going to put S. I'm going to go 10 minus 4. And then S minus B, 10 minus one of the other side lengths. So I'm going to go 7. And then S minus C, so 10 minus the final side length, which is going to be 9. And the order in which we multiply doesn't matter, right? A multiplication is commutative, so it doesn't matter what we choose for A, or B, or C. Now it's evaluating from here, and if you wanted to go into your calculator, you could do that. I'm going to go a little without. 10 minus 4 is 6, and then 10 minus 7 is going to be 3, and then 10 minus 9 is going to be 1. So that's going to be 180. So we're looking at the square root of 180. It means we're going to have to go to the calculator anyway to approximate our area. So let's just put the whole thing in there. I have trust issues, so don't mind me. It's trust with myself. Okay, it's late at night. If you guys had any idea what I was teaching all day long, my brain is like scrambled eggs sometimes by the end of the night. Okay, so 13, and let's just to make sure my math was not off here. Okay, good. Yay, I can multiply and subtract. Hallelujah. So the square root of 180 is going to be about 13.4. So that's going to be about 13.4, and this is area. These measurements were in meters, so we're going to say about 13.4 square meters. Okay, so thank you, Huron, for that lovely formula, and we can thank some other mathematicians for our law of sines and cosines, because now we can solve triangles, right? Yay. So hopefully you've got enough to get going on your practice. The practice isn't going to be too involved. So like I said, you should be okay there. But if not, you need some extra help, I am here for you. So just reach out. Till next time, take care.